Hey everyone, welcome back to the very last major topic of Calculus 1, which is the topic of concavity. Concavity. So we'll start off in similar to familiar territory. Here I have a graph of f of x, my normal f, and it looks like so. But now the difference is that onto the graph of f, I have put these little line segments that stand for the instantaneous slopes at those points. So let's say instantaneous slope here, let's say that's probably, let's say negative 10, pretty negative, right? Let's say negative 10, that goes to negative 9, negative 7, I'm just making these numbers up, negative 7, negative 3, 0, positive 1, positive 3, positively 5 sloped, positive slope of, let's say 7, and let's say 8, but then the slope starts doing what from here?
The slope starts decreasing even though it's positive.
Yeah, even though it's positive, it goes, let's say, from 8 to 7, to a slope of 5, to a slope of 3, to a slope of 0, to a slope of negative 1, negative 2. I'll get to that in a minute. But for now, at least from here to here, that's why I denote these slopes in blue. What is the graph? What are the slopes doing from here to here?
The slopes are increasing.
The slopes are increasing, which is just another way of saying what function is increasing from there to there.
The second derivative?
No, slope stands for which derivative?
The first derivative, yeah.
Yes, so we can say f prime is increasing on that segment of the graph. Make that a little nicer. Like so. Now, let's say it was positively sloped here at 8, and it goes to being positively sloped 7, 5, 3, 0, negative 2, negative 3, negative 5, negative 7, negative 9, negative 10, and then I'll say it stays negative, but it goes from negative 10 to negative 9. So what is the graph doing in terms of its slope properties from there to there?
So that is when the first derivative is decreasing.
The slopes are decreasing, right? Because again, positive 8, positive 6, positive, again, making numbers up here. Positive 3, 0, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, and then it starts doing something else from there. But on here we can say the slopes, i.e. f prime, is decreasing. Yes?
Yep.
Now then finally, from here onwards, your slopes are doing what?
It's back to increasing.
It is back to increasing. Those little blue line segments are increasing in steepness. And make sure you can see that those segments are increasing in steepness. So we can say on this piece of my graph, on this piece of f, plain old f, f prime is increasing. Now let's back up a minute to last lesson. Last lesson, when we said that plain old f, when plain old f was increasing, we said that had to mean the sign of f prime was what?
Positive.
Positive. Plain old f is increasing, sign of f prime is positive. Likewise, if plain old f was decreasing, the sign of f prime was
Negative.
right. Well, now just extend the analogy just the next level down. If f prime is increasing, then the sign of f double prime, the second derivative, is what?
Is also increasing, or positive. The sign is positive.
Sign is positive. No, we reserve the word increasing for the function right above it,
Okay.
so to speak. So again, plain old f from last time, if that was always increasing, then f prime was positive on that piece. If plain old f was decreasing, then f prime was negative.
So if something's increasing, then the derivative after that is positive.
Exactly. And vice versa for decreasing too.
Gotcha.
So f prime is always positive. F double prime here is always positive. Likewise here, what can I write?
F double prime is negative.
Yes, it's always negative. Okay, here or there, it's always negative on that piece. And finally, for this third piece, if f prime is always increasing for that piece, f double prime is always negative.
Positive.
Oh yes, good catch. Always positive on that piece.
Okay, so I have a question.
Yes.
Even though I see some red lines that have positive slopes, so you can have a positive derivative that's also decreasing at the same time, right?
Yeah.
Okay.
On here, the slopes are decreasing,
Yeah.
right?
Right.
Just like you can have a positively valued function, just regular function f, that's still decreasing.
Gotcha.
Let's say it's in the first quadrant, it's always positive, but you can still have it always decreasing.
Okay.
Let's say a piece of the line y equals negative x plus 3.
Okay.
All right, that function is always decreasing.
Right.
Even though part of it's in the first quadrant, it's always decreasing.
Oh, I see now. Yeah.
Yeah. Now, visually, what this means, the way we refer to these things, if it's a piece of an upward-facing U, we call this a concave up piece of a graph. Yeah, it's a piece of an upward-facing U. Likewise, for the second piece, what do you think you're going to call this?
Is that convex or concave down?
Concave down. It's a piece of a downwards facing.
Okay.
Just needs to be some approximately downward piece of a downward facing U.
Is this concave word the same as like concavity and like something, whether something's concave or convex? Does it shape?
Don't think about the word convex. The word convex doesn't appear.
Okay.
It's either concave up or concave down.
Gotcha.
And likewise here, this whole thing
Is concave
are
up?
the hallmarks for your piece of the graph being concave up. Concave up. Now then, let's focus for a minute on the sign of f double prime.
Okay.
For this entire piece, f double prime was
Positive.
positive, but then it transitioned into being
Negative.
negative. And so if this is a nicely behaving function, which it is, and this right here is what's called the transition point, i.e. a point of inflection. A point of inflection, by the way, is where the concavity of your planoid function changes. So here it transitioned from being concave up to concave down. And then about right here, the graph transitioned to from being concave down to concave up. You call those places of transition, those places of swapping of concavity, the points of inflection. Now then, what I was saying before, if this is a nicely behaving graph, which it is, the sign of your second derivative went from being positive to being negative. So what do you think its value was at the point of inflection? At the transition?
The second derivative?
Yeah, second derivative.
It's gotta be 0. Right?
Yeah, most of the time it's going to be 0. So yeah, if it went from being positive to being negative and it's a nicely behaving function, then you can think of this graphically. That only happens if you cross the x-axis for that derivative. So if something is a point of inflection, then the second derivative at that point, I'm using the letter x naught, that's going to be 0. Yes? But I'm very careful to note, this is not the only way you can have a second, this is not the only way you can have a point of inflection. For example, let's see. Consider the graph y equals x to the 1/3. Let's say f of x equals x to the 1/3. This graph, by the way, looks like this. Okay? First derivative is 1/3 x to the negative 2/3, right?
Yes.
And the second derivative is going to be negative 2/9,
X to the
negative
5/3, right?
negative 5/3, yes.
Huh.
And we can rewrite that as f double prime is negative 2 all over
9 times the cube root of x to the 5th.
Yeah, cube root of x to the 5th. So, clearly we can see visually that from here to here, is the graph concave up or concave down? Is the u facing up or is the u facing down?
That's concave up.
This is concave up. Likewise from here to here, from the origin on outwards. Is that a piece of a U that's facing up or facing down?
It's facing down.
That's facing down, so this is concave down. But is the second derivative ever 0?
It's undefined at 0, but...
Yeah, but it itself is never 0.
Right.
But it's undefined at 0, so another way you can have a second derivative, another way you can have a point of inflection, because again, right here, the graph transitions from being concave up to concave down. That is the hallmark that fits the definition of a point of inflection. So we definitely have a point of inflection there. It's just that the second derivative evaluated there is not 0. Okay. So f double prime can be either 0 or what?
Undefined.
Or undefined. And by the way, just for the sake of completeness, you can't have a function, like a piecewise defined function. Let's say, concave up here, and bam, you do some weird piecewise thing, and you get a sharp point right there.
That doesn't count as a point of inflection?
That does.
That does, okay.
Yeah. So, but I mean, I'm drawing this to show you that even though we have a point of inflection there, the second derivative, the second derivative isn't 0.
Okay.
Because the first derivative isn't 0, we have no tangent.
What about graphs with vertical asymptotes, like 1 over x?
So 1 over x is concave down in quadrant 3.
Concave down into 3, yeah.
Quadrant 3. Concave up in quadrant 1.
Right.
But it's not a point of inflection. Remember, it's a point on f of x,
Okay.
where the concavity changes. It has to be a point on the function.
Gotcha.
And we have no point on the graph of y equals 1 over x.
Okay.
Where that swap changes. We have an asymptote. We have different intervals of concavity.
Mm-hmm.
From negative infinity to 0, that graph is concave down. From 0 to positive infinity, the graph is concave up. So we have a change in concavity, but we don't have a point of inflection.
Okay.
We can have changes in concavity, by the way, without having points of inflection.
Gotcha.
And that's a good example. So good.
Okay.
Good. So key computational takeaway is that if this is a point of inflection, then the second derivative evaluated there is either 0 or undefined. But I cannot stress this enough, this implication, this statement, is not necessarily true in reverse. In other words, if your second derivative at a point is 0 or undefined, that doesn't necessarily mean that that point is a point of inflection. And I'll get to an example here in a second. But the way you determine whether this x coordinate here, x naught, whether it corresponds to a point of inflection or not, is you have to do interval testing with that value. So first you find where the second derivative is 0 or undefined, but you can't just immediately conclude from there that that is a point of inflection. You gotta fall back into interval testing. So, any questions so far? Let us migrate on over to the opposite side of the world. To illustrate that last point, that just because the second derivative is 0 or undefined somewhere, that does not mean you have a point of inflection. Case in point, the graph of x to the 4th. What does this look like?
Basically x squared, but sharper.
Yeah, sharper, and actually, it's actually flatter from 0 to 1.
Oh,
Then it shoots up very rapidly.
gotcha.
And likewise for 0 to negative 1. Shoots up very rapidly, like that. Visually, is this graph always concave up or concave down?
It's always concave up.
Yes, it is concave, it is concave up everywhere. If it's concave up everywhere, concavity never changes, so the second derivative, f double prime, is always what kind of value? Positive or negative?
It's always positive.
Always positive. Positive second derivative on an interval means the graph of f is concave up on that interval. However, if I compute the second derivative for this guy, let's see here. First derivative is 4x cubed, which makes the second derivative
0. Well, second derivative of 12x squared.
12x squared, and that equals 0. We don't have to worry about the undefined case, but this equals 0 when
X is 0.
when x is 0. But 0 f of 0 is clearly not a point of inflection, because to be a point of inflection, the point needs to be a place where the concavity inflects, where the concavity changes. This is not changing concavity, it's always concave up. So that's one way we know that this is not a point of inflection. But now, what if you didn't know what the graph of this looked like? What if you just knew this right here? You just knew the function, you knew the first derivative, and you knew the second derivative. How can you just determine purely computationally that 0 f of 0 is not a point of inflection?
Would you have to do something similar to what we did in the last video, where we test the left side to see if it's positive and test the right side to see if it changes signs?
Right. Yeah. We get this value, which I'm not going to call this a critical number. I'm going to call it a possible point of inflection. Our critical numbers we usually reserve for values that make the first derivative either 0 or undefined, but we're dealing with the second derivative. So I'm just going to say this, instead of a critical number, I'm going to call this a possible point of inflection, or a possible x-coordinate of a point of inflection. So you do the same sort of thing. You take that value, you look at the overall domain of your original function, and you slice up that overall domain with this possible point of inflection. Negative infinity to 0 and 0 to positive infinity, yes?
Yeah.
So help me out here. What is the sign of f double prime on this interval? Remember, we don't have the graph, we just know f, we know f prime, and we know f double prime.
Well, if f double prime has an x squared in it, then the left's got to be positive, right?
Right. F double prime is 12x squared. 12x squared is always positive on that interval, so yeah. Positive. Likewise here. This is from 0 to positive infinity. You take any number from in here, throw it in your second derivative. What kind of number do you get?
Positive.
Positive as well. And just like last time, we have a separate row for the behavior of f, plain old f. The second derivative being positive means the concavity there is what?
Up.
Up. So we'll say concave up. Likewise for the following interval, the concavity on that interval is also concave up. Do you see a transition in concavity from here to here?
No.
No. So conclusion, there is no transition. So 0, f of 0, is not a point of inflection, which I'll abbreviate POI. And of course, 0 f of 0, simplified as
0, 0.
0, 0.
Yeah.
It's not a POI because you do not see a transition in concavity. This again is how you would do it if you didn't have a graph in front of you. Make sense? Any questions?
So even though points of inflection and critical numbers work similarly, they're completely different things, right?
Yes, geometrically, visually, they are totally different things.
Okay.
The critical numbers are referring to your first derivative. Possible points of inflection are referring to your second derivative.
Okay.
The first derivative is reporting on the slope of the graph. Second derivative is reporting on concavity. So everywhere on this graph is considered a place of upwards concavity. But clearly not everywhere on this graph is a place of the same first derivative, right?
Right.
First derivative is negative from there to there and positive from there to there.
Okay.
But it's always the same sign for the second derivative.
Yeah, so we have a relative minimum on that graph, but we don't have an inflection.
Right.
Gotcha.
So here I am not given a graph, I am given a function, and I want to just find the points of inflection of that function, determine the intervals of concavity of that function, and having all that information, I then want to sketch a pretty good graph of f. How can I find the points of inflection? Computation. It's the first thing I have to do.
You gotta take the second derivative.
Gotta take the second derivative, which requires that I first have the first derivative. F prime, in this case, is that, which would make the second derivative what?
12x squared minus 24x.
Yes, my friend, 12x squared minus 24x. That thing, I can simplify a little bit. I can pull out a 12x to give me x minus 2 left over. And I set him equal to what?
0.
To 0. I want to find this when this is 0. Clearly that happens when x is 0 or x is
Undefined. But, oh, 2.
2. I know, this thing is never undefined.
Yeah.
This is a very nice polynomial.
Right.
It's never undefined. This happens when x is either 0 or 2. So those, again, I don't call them critical numbers, I call them possible points of inflection, or more accurately, possible x-coordinates of my possible points of inflection. But whatever you want to call them, what do I do with these?
We gotta test the intervals between all of them.
Right, I take those points, I slice up my entire domain of my original function, which is, in this case, is negative infinity to positive infinity. So coming over here, slice him up, and what do we get? Let's see. Left to right, reading it left to right, I get negative infinity to 0, 0, 2, and to infinity, yes?
Yep.
And I'm interested in two things. The sign of f double prime, and what does that mean for plane old f?
The concavity.
Yes. Make a nice little table like so. And now start testing. Pick a number from in here, throw it in your second derivative. But by the way, when you're testing for intervals of concavity, or intervals of anything really, and you want to test numbers, is it easier in general to throw it in the unfactored expression or the factored expression?
The factored, I guess.
Right, because if it's factored, the main operation is multiplication.
Multiplication, yeah.
And moreover, the terms are relatively easier.
Oh, so that way you can see the sign.
Yeah, exactly.
Got
You say this, you can see the sign. So let's say I take negative 10. If I throw it in right here, I get 12 times negative 10, which is
Negative.
negative. Negative 10 minus 2 is
Negative.
a negative times a negative
It's positive.
is positive. So f double prime is positive on this piece of the graph.
So we test the intervals within the second derivative, not the original function.
Right, because we're trying to find the points of inflection
Yeah.
and the intervals of concavity.
Okay.
Yeah, this question's not asking for determine the intervals of increase or decrease of f. It's asking for the intervals of concavity.
Okay.
So f double prime is positive on this piece, which means what in terms of its visual representation on the original?
It's concave up.
Concave up. Likewise, from 0 to 2, let's say 1. If I take 1, I throw it in my factored form of the second derivative, I get 12 times 1 times negative 1.
So that's a negative.
That is a negative. Second derivative is negative on that piece, which implies that the plane old f is
Concave down.
concave down on that piece of the graph. Absolutely. Final interval 2 to positive infinity. Take a really big number, you stick it in here, that's also going to be
Positive.
positive. Positive, positive, or positive, negative, positive. In this case, geometrically, that means it's concave up. Plane old f, the original graph, original function, is concave up on this interval. So with that, we're actually done with the second part of the question. Determine the intervals of concavity. All you guys got to do is just, we can use a different color if we want. Hey, it's concave up on this interval. Likewise, it's also concave up on this interval, yes?
Yeah.
You can do the same thing. I'll do a different color here. It's concave down on this interval. And with that, we are done with determining the intervals of the concavity.
Cool. So that they're all, that means they're both inflection points, right?
Why? Because you see what?
A change in concavity.
You see a change in concavity. The key word there is a change in concavity. From being concave up to concave down in the first case, concave down to concave up, concave up to concave down in the first case, and then concave down to concave up in the second case. So because there is a transition, So unlike in the previous example where we had no transition, left to right, here we have transitions galore. Because we have, well, not a transition.
We have 2 transitions.
Yeah, so not only is 0 f of 0 a point of inflection, but so is,
2 f of 2.
yes. Will we be more English-like and put an is there? So 2 f of 2. And finally, we can just throw those values into the original function. 0 f of 0 is
Just 0, 0.
just 0, 0, and 2 f of 2 is
16 minus 32, so negative 16.
negative 16. Those are your points of inflection. There. So with that, we are done with the points of inflection. Okay, final thing is to graph this guy.
Are you expecting us to graph this like by hand or?
Yes.
Okay.
Now, with everything we know now from Cal 1, you know, we're using second derivative properties from this lesson, first derivative properties from the previous lesson, and also you still have your knowledge from pre-Cal foundations, finding asymptotes, horizontal, vertical, and behavior as well. We're going to have all these things marshaled together at the same time to provide some accurate hand sketchings.
Cool.
So let us first let's put these points on the board. 0, 0 is right there. Let's say here's a 2. I can just put negative 16 somewhere down there. I know from 0 to 2 that the graph is what kind of shape?
Concave up.
It is concave up. Yes.
Wait, concave down, my bad.
So 0 to 2, yeah, concave
Yeah.
down. So it's a piece of a downwards facing U, yes?
Yeah.
And now, let's find where the first derivative is 0.
Okay. You can factor out of 4x squared.
Factor out of 4x squared, so I'm left with,
Minus 3. So that's at 0 and 3.
right, so this thing equals 0. When x equals 0 or 3, in other words, at 0, and somewhere at 3, which by the way I know is going to be somewhere down here, yes? I know my slope has to be 0 there. Right?
Yeah.
Now let's bring concavity back into the picture. From 2 to infinity, the graph is always
Concave up.
always concave up.
And it will be 0 at 3, 0. Or it will be 0 at 3 f of 3. The slope.
Right,
Yeah.
because of that. Now, that's it for our calculus knowledge. How about our pre-cal knowledge? What is the end behavior? As you go from 3 to infinity, is this graph shooting up to infinity, or is it leveling off? What is it doing?
It'll be shooting up to infinity.
It shoots up, so I shoot it up to infinity. What's my end behavior all the way to the left? If it's getting more and more and more negative, what's that doing?
Since you have an even exponent, it will also shoot up to positive.
Also shoots up. So this is just pre-calculus knowledge. Foundation knowledge also shooting up to infinity. And look, with that, we have provided a pretty good accurate sketch of this graph by hand.
Oh, nice.
We have implemented pre-calculus knowledge with our newfound knowledge of calculus in terms of relative mins, relative maxes, and now concavity. So it's all coming together.
So if we're given problems to graph by hand, should we find both the points of inflection and the critical numbers to improve our accuracy? Would that help?
Yes.
Okay.
Yes. And I'll give you guys some more graphing problems here in probably another video. But for now, let's just leave it like this.
Okay.
Everything good so far?
Yeah.
Cool. Okay. Okay. A bit of a harder one. Same instructions. Find the points of inflection, find the intervals of concavity, and then sketch a graph, which is going to potentially use our first derivative knowledge as well. Okay, I'm just gonna derivatize for a bit.
Is that a word, derivatize?
I like it, so it is.
Okay.
Low d high minus high d low all over low squared. Just a nice negative 12x over that same denominator.
Oh boy, the second derivative is going to be fun.
Oh, it is all sorts of fun, let me tell you. Low d high this. Minus high d low. So chain rule that low. Like so. That's all over the bottom squared. Now we have x squared plus 3 to the 4th, yes?
Yep.
Yes. Let me tidy this up a little bit. That minus negative 12, I can turn into
A plus 12.
just a plus 12. Let's get rid of some of these parentheticals like that.
Yeah.
Okay?
You can divide both sides by x squared plus 3 or x squared plus 3.
Yeah, or I'm gonna factor out
Okay.
all the x squared plus 3 I can. So from the top, here I have an x squared plus 3 to the second. Here I have an x squared plus 3 to the first for the second term here.
Mm-hmm.
So the number of x squared plus 3 that I have in common,
Just one.
yeah, just one, x squared plus 3. Factor that out, I'll put the leftovers in brackets. That is negative 12 times 1x squared plus 3. Plus 12x. All times 2 times 2x, yes? All over x squared plus 3 to the 4th. What can I do now?
You can divide. You can cross out 1 x squared plus 3.
Look, we have a murder. That goes away. We're left with 3 of them over here.
Yeah.
So in total, we have how many? Well, I just said the answer. 3 on the bottom. Now let us, just to save on a bit of board space, what is this bracketed term? Let's do a little bit of that here. That is negative 12x squared minus 36 for that first term. Yes?
Yeah.
2 times 2x is
4x.
4x. What's 4x times 12x?
48x squared.
Plus 48x squared. So all in all, I have,
36x squared minus 36.
look at that, I get some very nice numbers. 36x squared minus 36, which of course I can pull out of 36. Yes?
Yep.
I'm left with x squared minus 1 on the top. Of course the bottom stays boring, stays vanilla, stays the same. That's fine. The top, I can do what?
Factor that binomial factor. X plus 1 times
Plus
x
and minus 1. Precisely.
Oh.
And now, there's my final factored form. Now, I need some room to gallop for my graphing and my interval testing and all that good jazz. So I am going to erase all this and put that over here.
Okay.
F double prime. Negative 36. X plus 1. Minus
It's
1.
positive 36, I think.
Oh,
Yeah.
you're right. That's my second derivative, and my first derivative too, I'm gonna just rewrite that. A little closer here to the left side. It's negative 12x all over x squared plus 3 squared. Now help me out. I want to find possible points of inflections and intervals of concavity. So I have to set my second derivative equal to what?
0.
0 or?
Undefined.
Undefined, but is this ever undefined?
It can't be. Yeah.
Right, x squared plus 3 is always what kind of number?
It's gotta always be a positive number.
Always positive. You cube a positive, stays positive. So this whole thing is never undefined.
Okay.
But it is 0 when what is true?
X is 1 or negative 1.
Precisely, friend. X is 1 or x is negative 1. So I take these possible x coordinates of possible points of inflection and I do what to them?
You test the intervals like we did last time.
Right, you split your entire domain of the original into intervals. What's the entire domain of this? What is the domain of my original function?
Negative infinity or positive infinity.
Right, this is never undefined.
Yeah.
X squared plus 3 guarantees that the bottom is always positive. So this is a nice negative inf to positive inf. Split that guy up. And yeah, I'll do that here. Like so. There's my sine of f double prime. Here's my behavior plane of f. Now let's take it piece by piece. Pick a number on this interval.
Okay.
It's a negative 100.
Okay.
If I stick negative 100 into my second derivative, what kind of number comes out?
You'll have a negative on them. Both exponents on both binomials. So it'll be a negative times a negative, so it'll be a positive.
So this will be negative, right?
Yeah.
Negative times a negative
Yeah.
times positive 36. We already discussed that the bottom of this is always
Positive.
positive. Okay. X squared plus 3 is always a positive number. Cube positive stays positive. So we don't need to worry about the bottom at all.
Yeah.
Okay? Bottom's always positive. We don't need to worry about the 36. It's always positive. So we just need to worry about what is the product of these last two terms doing.
Okay. And yeah, they'll both be negative.
So they'll both be negative.
So it's positive.
So positive. Absolutely. All right. F double prime being positive on that interval means that F on that piece is
Concave up.
concave up. Likewise here, what's a nice number between -1 and +1?
0.
0. You stick 0 in here, you get
A positive and a negative.
positive and then a negative. Positive times a negative gives me
A negative.
a negative. Of course means that's concave
Down.
down. On that piece and final piece, stick a really big number in there, you're going to get
A positive.
positive. 36 times a positive divided by a positive is
Positive.
absolute. So concave up, and with that we are done with finding intervals of concavity. I'll indicate my intervals of concavity for concave up with red. That corresponds to that and that. And I guess I'll do blue. Concave down corresponds to this interval here, yes?
Cool.
Now then. Last thing is to try to graph this thing.
Do we need to define the points of inflection?
Oh, that's true, we need to do that.
So they're both going to be points of inflection because they're both changing.
Right. We have a transition from being concave up to concave down at x equals -1. And the graph transitions from being concave down to concave up at x equals +1. So these are both POIs. And precisely because we see a change in the sign of our second derivative, we see a change in concavity. All right, let's get the points for this. What is -1 f of -1?
We plug that in the original function, eh?
Right, POIs are points on the original.
Right. So that'd be 6 over 4. So yeah, just 3 halves.
-1, 3/2 for the first one, and for the last one,
Same thing, -1. Oh, positive 1, 3 halves.
+1 and 3/2. Those are my points of inflection. All right, let's try graphing this, which might require some first derivative knowledge as well, but let's give it a go. So I have 2 points of inflection. Let's put those on the board. -1, +1, and 3/2, let's say about right there. They're level, right?
Yeah.
They're both at 3/2. That level? Almost. Okay, let's incorporate some first derivative knowledge in here.
Okay.
Let's see if there's any, if there are any relative extrema. Is this thing ever 0 or undefined?
Yeah, it's 0 when x is 0.
Right. 0 when x is 0, so I know, let's see, when x is 0, my original point is
6/3, so 2.
right. There's a 2. So I know right there I have what kind of slope?
Yeah, slope 0.
I have a slope of 0, indicate that in red.
And since the concavity is concave down to you, then that's gotta be relative max.
Yes. So notice how we'll talk more about this in a bit. But I didn't have to do any interval testing with my first derivative to realize that this point was a relative max. It's all based on my second derivative knowledge of this being concave down. I know from -infinity to -1, in other words, the entire piece to the left, that's always concave up, right?
Right.
And I know that the piece from 1 to +infinity, that's also concave up. But you want to be careful here. You're not going to draw a full upwards facing U like that, a full upwards facing U like that, because of the following, because of a piece of your knowledge from pre-calculus. What is the end behavior of this graph? Let's start with +infinity. What's the rightmost end behavior?
As x goes to +infinity, then the graph is leading towards 0.
Right. In other words, you have what kind of asymptote?
A horizontal asymptote.
Horizontal asymptote at x equals 0. So even though this piece is concave up, it's a piece of some kind of upwards facing, that's too close to the x-axis. Even though it's a piece of some kind of upwards facing U, it's kind of it's a U that never comes back up. Does that make sense?
Yeah.
So it's like the first half of a U almost.
Mm-hmm.
And that last bit of that first half just kind of goes on and on forever.
So its slope will always be increasing, but increasing incrementally.
It's always increasing, but it's never going to be 0,
Yeah.
right? So like already here the slopes, let's say like -3-ish, -2, -1, -0.5, -0.4, -0.03, -0.01,
Gotcha.
and so forth. Likewise, from -1 to -infinity, I also have a horizontal asymptote there. So again, notice it is concave up. It is, think of it like a mouth. The mouth is facing up. It's not facing down.
So it is symmetrical, right?
Yeah. It's a little bell curve thing.
Nice.
It's a nice little bell curve graph. So when you're graphing these, don't forget your knowledge of pre-calculus. You want to test for asymptotes, including horizontal asymptotes.
Okay.
Make sense?
Yeah.
Any questions? Okay, everyone. One more problem like this. Same instructions. Find the points of inflection. Find the intervals of concavity, and then find a good graph. Sketch a good graph. Take them to the top again. Find the first derivative. So low-D high, high-D low, this stuff. Let's see.
Are we going to simplify the first derivative too?
Oh, of course. We want to simplify. Otherwise, finding critical numbers, finding possible points of inflection is it's a real pain.
Okay.
If we don't simplify. So let's see. That is going to be a 4x, 2x cubed, right?
2x cubed.
2 times x squared.
Oh, okay, yeah. 2x cubed minus 8x.
Minus 8x.
Minus 4x. 2x.
Minus 2x cubed.
Minus 2x.
Minus 2x. Look at that. Those go away, right?
Yes.
I'm left with a nice
Negative 10x. Okay.
negative 10x up top.
Oh, that's going to be easier to take a derivative of.
Absolutely. Absolutely. Now push rule, low-y high, high-y low, low squared that bad boy. We get something that goes like so.
Negative 10 times x squared minus 4, the whole thing squared, minus negative 10x times that mess, which is 2 times all that times 2x, yeah.
That's 2x. All over the bottom squared, right?
Yeah, so to the 4th.
So to the 4th, so it looks like we're going to have to do some similar algebraic technique as we did on the last problem.
Okay.
When we found the second derivative. Alright, let's see. First, I gotta have a negative negative. I can simplify that into
Positive.
a nice plus 10x. Just getting rid of some parentheses. And now we pull out some commonalities. Pull out a...
A 10 and an x squared minus 4.
Sure, I can pull out a 10. So I'm gonna go ahead and pull out a negative 10 so I don't have a negative up front.
Okay.
I can pull out a negative 10 and x squared minus 4. Negative 10 times x squared minus 4, and the leftovers, I will bracket that. So I'm left with just a single lonesome x squared minus 4 for the first term, and for the second term, what do I have?
2 times 2x? Yeah.
Well, I had that plus 10x there. I put out a negative 10.
Oh, yeah.
So I have
So, x times 2 times 2x.
x times 2 times 2x. Exactly.
Yeah.
All over that to the 4th. And now look, this goes away. I have 3 on the bottom. Now what do I have going on up top?
Let's see. It would be negative 10 all times x squared minus 4. And that's negative 4x squared on the right.
X squared minus 4.
Minus 4x squared. Okay?
Minus 4x squared.
Yeah.
Okay, so all in all, I have how many x squared minus 4s?
You have
I'm sorry, x squared minus 4. How many x squared do I have?
negative 3x squared.
So I have negative 10 all times.
Negative 3x squared minus 4. And that turns out to be 30x squared plus 40.
So that's what we have up top. So we stick that back in here and we get 30x squared plus 40, all divided by x squared minus 4 to the 3rd. Ooh, and I'll tell you what, I need some room to gallop with my interval testing and with my graphing. So let's nerf all this.
First derivative 2?
No. Do you remember what it was?
Yeah, it was negative 10x all over x squared minus 4, the whole thing squared.
That was my first derivative, and my second derivative, of course, is this right here. Now let us analyze that second derivative. Firstly, can that ever
The second derivative is x squared minus 4 cubed on the denominator.
cube on the denominator? Okay,
Yeah.
gotcha. Okay, possible points of inflection. Let's start off by looking at our second derivative. Let's actually start off with seeing whether it can be undefined. Can this thing be undefined anywhere?
Yeah, at x equals 2.
2, but remember, we're testing for possible points of inflection, which need to be points on the original graph,
Right.
which means we have to look at the domain of the original.
Okay.
So if the domain of the original is undefined at,
2.
in other words, 2 and
Negative 2.
negative 2 are not in my domain of the original,
Okay.
do I have to worry about those being possible points of inflection?
For the second derivative, no. Yeah.
No, I have no points of inflection.
Okay.
I have no points of inflection because negative 2, positive 2 aren't even in my domain of the original.
Got
So they can't be points on the graph. There's no point for the graph there.
Okay, is it because the vertical asymptote's there?
Yeah.
Gotcha.
So I don't need to worry about the undefined case for my second derivative.
Okay.
Can my second derivative ever be 0?
I don't think so in the numerator.
What kind of number is 30x squared plus 40 always going to be?
It's always going to be positive.
It is always
Greater than 40. Yeah.
always positive, right? I mean, x could be 0.
Yeah.
So it could be it's greater than or equal to 40. But this thing, wherever this the bottom, by the way. Let's see here. Yeah, top's always positive. So, do I have any points of inflection?
No.
No, because there are no places where the second derivative is 0 or undefined. And that was a necessary condition for having a second derivative. Sorry, for having an inflection point. Was that either one of those two things had to be true.
Okay.
So that, what were we going to say?
So how are we going to test what the graph looks like then?
Well, even though we don't have points of inflection, that does not mean that this thing is always concave up or always concave down. We can still have transitions in concavity. They're just not going to happen at points of inflection.
Okay,
Just
so
like-
the concavity can change depending on if the asymptote changes it? Or...
Yeah, if it changes at the asymptote. Remember the example you brought up earlier? Y equals 1 over x.
Yeah.
1 over x was concave down in the third quadrant,
Okay.
concave up in the first quadrant. Even though for that, there were no relative mins, there are no relative maxes, there are no points of concavity, points of inflection. We still had transitions in concavity.
Okay.
We transitioned from being concave down to concave up at the asymptote x equals 0.
Okay.
But there's no point of inflection because there's no point on the graph. Y equals 1 over x at x equals 0.
Okay.
So we could have a similar thing here going on with this. So we're going to do interval testing. Not with possible points of inflection, but with,
Asymptotes?
yes, with vertical asymptotes. Just like we did interval testing with vertical asymptotes when we did our first derivative test for increase and decrease, decrease and increase.
Gotcha.
Same idea here with vertical asymptotes.
So we're really going to need like pre-cal knowledge for this stuff, right?
Oh, absolutely.
Gotcha.
It all builds on each other. What are the vertical asymptotes?
-2, f of -2, and +2, f of +2.
X equals -2 and x equals +2.
Yeah.
So I take these, I partition my interval,
Mm-hmm.
right? My domain. -infinity to -2, -2 to +2, and 2 to +infinity. By the way, if I had possible points of inflection and I had vertical asymptotes, in this case I had no possible points of inflection, but if I did and I had vertical asymptotes, I'd have to use all of those numbers to partition my entire domain.
Okay.
Okay? In this case I had no points of inflection, so I just have to partition my domain by the vertical asymptotes, but the vertical asymptotes are already built into the overall domain. So there it is. There's my second derivative. There's my plain old f. Let us see what's happening. What is the deal here? If you take a number from inside here, let's say -100. We already determined that the top of this second derivative is always
Positive.
positive. So we don't really have to worry about it.
Yeah.
But the denominator is something I'm cubing. If I take a -100 and square it, subtract a 4, is that positive or negative?
It's positive.
Positive, cube it, stays.
Positive.
Yeah, you cube a positive, it stays positive. So the sign of the second derivative is positive here, which means plain old f geometrically, visually is concave up on this piece. Now on the following piece, -2 to +2, what's a nice number in there?
0.
0. Again, I stick 0 in here, stays always positive, but if I stick 0 in the bottom, I get -4
Q.
Q.
So that's negatives. And then, yeah, it's negative.
That is negative. So on that piece of the graph is
Concave down.
concave down. That is what it is doing visually. Concave down. Final thing, take a really big number, stick it in here. You get
A positive.
a positive number. 100, stick it in there. Becomes positive. Concave up, concave down, and final piece is facing up. It's a nice upward facing U. So for intervals of concavity, all I want you to do is concave up on that interval. It's also concave up on this interval. And finally, it's concave down on this interval here. That's it for intervals of concavity. Now, are these points of inflection?
No.
Right, we don't have points of inflection.
Right.
We have no points of inflection. That was something we determined at the very beginning. No POIs, because F double prime is never 0 or
Undefined.
undefined, or really undefined.
When F is defined.
Yeah, or undefined again. This is all on F's domain.
Yeah.
On the domain of plane order.
So that's it's a bit tricky how concavity can change, but you can still have no inflection points. It's something to look out for.
Something to watch out for, but I mean, as long as you remember the point of inflection is by definition a point on the original graph, then of course, you can't have a point of inflection at an asymptote because there's no point there.
Gotcha.
But you can have concavity changing.
Okay.
So we do have intervals of concavity, different concavity, but no points of inflection. Make sense?
Yeah.
Okay, what about the graph of this thing? What does that graph look like?
Boy.
All right, let's get rid of this.
It's gonna be a line. It's gonna have a shape. It's gonna do some stuff.
It's going to do some stuff for sure. The question is, what is the nature of that stuff?
Would I get credit if I just said that?
If what, that it did stuff?
Yeah, it's a line that does stuff.
You'll get negative credit.
Okay.
No, I'll give you below 0 if you do that.
Nice.
Ooh, okay. Let's see, what can I do?
We need to find the horizontal asymptote as well, right?
So far what we've been doing for graphing is we first put up the points of inflection.
Then the critical numbers, right?
Yeah. So first, points of inflection. Are there any points of inflection here?
No.
No. How about relative mins, relative maxes? Can my first derivative ever be 0?
I think so.
Yeah, this thing equals 0.
When x is 0.
When x is 0,
And what is that?
can it ever be undefined?
Yeah. Wait, yes?
It's not undefined though
It's not
on the domain
Yeah, it's not undefined on the domain.
of the original. So we don't have to worry about the undefined case.
Gotcha.
So what is 0
F of 0.
f of 0?
It's negative. It's 1 over negative 4, right? So negative 1/4.
Yeah, negative 1/4, so I know. So here's negative 1/4. I know that the slope there has to be 0. Now, even though I can't graph points of inflection because I don't have any, I can still graph the transition areas, transition spots, from where it goes from concave up to concave down and concave down to concave up, because at those spots we have what kind of objects?
Asymptotes?
Right, at x equals -2 we have a vertical asymptote. And at x equals +2 we have
Another vertical asymptote.
another vertical asymptote. So rather than points of inflection serving as the places of transition, we have vertical asymptotes serving as the places of transition. Okay?
Okay.
Okay. Cool. Alright. Now then, from -2 to +2, the graph is always doing what?
Concave down.
It is being concave down.
So that means that's a relative max?
Yes.
Nice.
Okay. How's about from 2 to positive infinity? This graph is always
Concave up.
concave up, so I know.
It starts at positive infinity? Yeah. Okay.
Now the question is, do I have a full U or just part of a U?
I think we need to test for horizontal asymptotes, eh? See if we have any.
Yes.
Yeah.
What is the limit of this thing as x goes to positive infinity?
It's gonna be 1 over 1. Yeah, it's gonna be positive 1, right?
Yep.
Because the exponents are the same. Is that what it was?
Yep, that was it. X equals y equals 1. But what about as x goes to negative infinity?
I mean, it's the same both ways, right?
Remember, sometimes we can have 2 horizontal asymptotes.
Yeah.
But do we have 2 in this case?
No.
No, whether you go all the way to the right, limit it as to positive infinity, whether you go all the way to the left, limit it to negative infinity, you still get a value of 1.
How can you get 2 horizontal asymptotes again?
We're going to see one like that later.
Okay.
I mean, for now, you could have something. There are a lot of graphs that look like this.
Gotcha.
One right there, one right there.
Okay.
But this is not this case. This is not that case. This case, we just have one horizontal asymptote. At 1. So this graph is never hitting 1, right?
No.
It's always getting closer and closer to 1. Slope is always increasing from a negative value to being less and less negative, approaching a value of 0. Slope is increasing, but it's never getting to the other side
So
of the
the
U.
slope is increasing even though the graph is decreasing.
Exactly.
Okay.
I mean, plain old f is decreasing, right?
Yeah.
But the slope, here let's say it's negative 10. Now it's like negative 5, negative 3, negative 1, negative 0.1, negative 0.01, negative 0.001, negative 0.00001. But no, it's never hitting 0.
Yeah.
So it's like just half of the upward U. You can think of it like that. And of course, same deal. So, key takeaways, big picture stuff. When you're graphing, start with your calculus knowledge first. Your concavity, your relative extrema, but don't forget to incorporate your pre-calculus knowledge as well. Horizontal asymptotes, vertical asymptotes, and end behavior, which is really encapsulated in horizontal asymptotes, right?
Okay.
So all your knowledge needs to be thrown at these problems. Any questions?
Okay.
Cool. All right, let's try a different one. This is more of a detective type problem. It requires you to sketch a graph so long as you satisfy these 5 properties. F of 4 equals f of 6, which equals 0. The first derivative is always positive. Whenever x is less than 5, the first derivative doesn't exist at 5. And the first derivative is negative whenever x is greater than 5.
Okay.
And finally, the weirdest one is that the second derivative is always positive except at 5.
Okay.
Let's do this piece by piece. Let's start with the first one. Easiest one. F of 4 equals 0 and f of 6 equals 0, yes?
Yes.
So I know I have a dot and a dot here and here, yes?
Yeah. That's supposed to be a 6.
Oh, that should be a 6. Now then, my first derivative is positive whenever x is less than 5.
No, less than 5.
My first derivative is negative whenever x is greater than 5. But f prime at 5 doesn't exist.
Okay, so it's got to be either a hole or an asymptote or a sharp point. So.
Exactly. Could be a hole, could be a sharp point, could be an asymptote.
Yeah.
So answer me this. Let's go with the sharp point thing. I'll do this in blue. Let's say we have a sharp point like that. Let's see, does that satisfy this stuff? Let's start with the first thing satisfied. Is the first derivative, is the slope positive from here to here?
Yes.
Is it negative from here to here?
Yeah. Is our domain negative infinity to positive infinity? Or
Yeah, if we want, we can keep going.
Okay.
You know, forever and ever like that.
Gotcha.
Forever and ever like that.
Nice.
Okay, so this graph definitely checks off first one, the second one.
Yeah.
The third one, there's a sharp point at 5.
Mm-hmm.
The fourth one, the slope's always negative from 5 onwards. Ugh, what about this? The second derivative is positive, i.e.
It's always increasing, always concave.
not increasing.
Oh, it's not. It's always concave up.
Yes.
Oh, we sketched a concave down graph.
Yeah, so what do we have to do?
What the heck? Okay, just flip it up across the x-axis. Yeah. I think. Right?
Flip it across the x-axis?
Flip it. I mean, flip it vertically, right? Did that do it?
Let's see. If you flip it vertically, so the problem is if you flip it vertically,
Oh, then it breaks the other rules. It's like Sudoku.
yeah. If you do it vertically, then even if you have a sharp point
Yeah. Then the other rules are messed up.
at 5, now my first derivative is negative
Yeah.
there and it's positive there.
Huh. Okay.
So that's not gonna work. So this one almost has it. The one in blue, the one we drew at first, it almost has it, but it's just violating that last condition.
Okay, just turn the whole thing concave up then. Just like,
You mean instead of going like this,
yeah, just go the other way.
like this?
Yeah.
That works. That is magical. Look at that. It's so weird but so fun.
You're not expecting us to like find the equation of this graph, are you?
No, just sketch.
Oh, thank goodness.
I have no idea what that graph is. You have to be some piecewise thing.
Yeah.
But yeah, this one in red, in purple and maroon, satisfies that. The first derivative, the slope is always positive to the left of 5, always negative to the right of 5. So it satisfies that and that. F prime of 5 doesn't exist, we have a sharp point. But now, unlike the graph in blue, this piece and this piece are both concave. Concave up. So there we go. There's our
What is
detector.
the second? Oh, the second derivative just doesn't exist when x is 5, right?
Yeah.
Gotcha.
We're not worrying about that case.
Yeah.
But we are worrying about all other numbers.
Cool.
Any questions about that?
No.
Okay.
Is that going to be the end of this first video?
Yeah, just plain old second derivative.